Local in, implicit map representation and localization with invertible neural networks. My name is Zirui. Robot localization is an inverse problem of finding a robot's pose using a map and sensor measurements. The reverse process of inferring the pose from sensor measurements is ambiguous. Measurements from multiple poses can be very similar. On the other hand, invertible neural networks such as normalizing flows has been used to solve ambiguous inverse problems in various fields. We propose a new framework to solve the localization problem with invertible neural networks. It stores the map data implicitly inside the neural network. It outputs uncertainty estimation from the neural network, and is capable of learning and providing localization for complex environments. We learn a bijective mapping between the poses and LiDAR scans with a series of invertible transformations. We use a conditional input calculated from the previous pose of the robot to reduce the ambiguity of the problem. The lost ambiguous information is captured by the latent space during training. During the evaluation, we can sample the latent space to find the full posterior distribution of the pose. We use an variational autoencoder to reduce the dimension of the LiDAR scans and use positional encoding to augment that of the poses. The network is trained with loss functions on both sides. We validated our method in experiments with 2D and 3D LiDARs. For 2D, we use 3 maps. We trained with data from the simulation I directly deployed on an F-110 car, which has a 2D LiDAR and a Jetson NX board. Here are videos of live localization on an F-110 car in a real environment. Because local in outputs a distribution of poses, we can further use an EKF to fuse with other sensors. We are comparing it with a particle filter. Results show that local in gives accurate localization with much lower latency. For 3D experiments, we use public datasets. We treated 3D LiDAR scans as range images and just added convolutional layers to the VAE for encoding them. Results show that the accuracy of local in is on par with the state of art. Here are examples of 3D map reconstruction. On the moron side, we can see just by training with 6,000 data points, the network is able to interpolate and reconstruct major features on a large map with test poses. We also provided an algorithm for global localization with local in. We randomly initialize a set of conditional inputs and use new LiDAR scans to narrow down the assumptions. The algorithm is tested in different environments, and the results show that the convergence is fast with low errors. Please see our paper for more details. Thank you.